So, so in this lecture, we will discuss the different properties of an amplifier. Till now, we have been discussing only one of the property of the amplifier, which is basically the gain. Okay. So other than gain, there are other properties of the amplifier. Of course, the gain is the main factor, but other than gain, we should also make sure that certain properties are met before we actually make a good amplifier. So other than gain, we have the voltage swing. Voltage swing means how large the input swing as well as the output swing can be, the amplitude that the amplifiers allow. Okay, so some amplifiers may have a high gain, but if the swing it allows is very small, so it may not be very usable. Okay, so we need to make sure that we have a large voltage swing at the output. So this is we will be discussing today. And of course, we have the input and output impedance of the amplifier. So these are also the important properties that we need to discuss. This input and output impedance plays a very important role, especially when we want to, drive particular load or if the input resistance of the source is small or large, so the input and output impedance of the amplifier affects that. Okay, so this also we will be discussing, and finally we will be discussing the bandwidth of the amplifier. So in this lecture, we will focus on the voltage swing and the input and output impedance. In the next lecture, we will discuss the bandwidth of an amplifier. So let's go back and revise the common emitter amplifier that we have discussed till now. Okay, so this is the common emitter amplifier. Okay, so the DC voltage of the V out, we know that VOUT. Okay, of course this is again V capital and the subscript capital. So this means the DC voltage is equal to VDD minus IC into RC. And if you remember, in the last class we have discussed that the gain of this amplifier, we know that if there is no source resistance, it is minus IC into RC by VT. Okay, so now here if you see the expression, okay, so if you see this expression of this gain, if I want to get a very good gain, I can increase my IC and RC because I don't have an option of increasing this VT. And IC and RC, if you know that it is the drop across these resistance, because the current flowing through this is IC. Okay, so now if I try to make the gain very large, what will happen is the voltage drop, DC voltage drop across this one will become very large, and it can force this transistor to go to the saturation region, because if the voltage here, VCE voltage, is lesser than 0.3, then my transistor goes into the saturation region. We know this one, right? So if my VCE voltage is lesser than 0.3, then this is the saturation region. For amplifier to operate properly, we want to keep it in the active region. So this is the minimum voltage that we can allow. Okay, so when VCE is lesser than 0.3 volt, then the transistor goes to the saturation region. So similarly for the voltage swing also, of course, this input will get amplified, and at the output I'll have a nice voltage swing here, right, the sine wave. So I should also make sure that the lower portion of this sine wave should not be lesser than this 0.3 volt. Okay, and of course if the higher portion, if you see the higher portion, if you see, it can go till VDD definitely, and the lower portion it cannot be less than 0.3 volt. Okay, So let's rewrite this one more properly. So if this is my V out, okay, this is my V out. V out basically both the AC and the DC, and the peak value it can go till VDD, and it can go as low as 3 volt, which is the saturation voltage. Okay, so if it cross beyond this VDD, if the swing is much higher than this, right, you will see that the waveforms gets clipped. Okay, because it goes to the region. For example, here it cannot go beyond VDD, and here when it becomes more than or lesser than 0.3, then it goes to saturation region, so the waveforms gets clipped. So we need to make sure that that the swing is limited here. So that's why this mid voltage, which is basically this V out, right? So this is my V out. So I need to select. So I need to select this IC and RC such that this V out stays in between the mid of VDD and 0.3. So it should be the mid of VDD minus 0.3. So let's note this down. So what we have seen is that we need to select IC and RC such that my DC value, or the V out, right? V out is equal to, or V out, which is basically VDD minus ICRC, should be equal to VDD minus VCE set voltage, which is 0.3. Of course, this is the VCE set voltage, okay, which is 0.3 by 2. So now maybe if the VDD is quite large, then VCE set by VDD maybe 10 volt, or it can be generally it is 10 volt or 15 volt. So I can approximate it to be VDD by 2. Okay, so my V out should be lying around VDD by 2. Okay, so this restricts the value of the IC and RC, and in fact this restricts the value of the gain as well. So I should try to place this DC voltage in close to VDD by 2. Okay, so now this is the maximum swing. Of course, if you see the amplitude wise, it's going VDD by 2 here and VDD by 2 here approximately. Okay, but in the real scenario, generally if you see here, we never go to this point. This is the maximum limit, so it may be lesser than that. Okay, so for safe side, for keeping the margin in the actual design, we'll make sure that the swing is reasonably lower than VDD in the upper end, and also in the lower side it is higher than the 0.3, to make sure that the operation of the transistor is working properly. Okay, so now this is in terms of the swing at the output. So now once we know the gain, right, so we know that the output swing here, it should be approximately VDD by 2. So then this will define how much should be the amplitude of my Bin that I can apply in this amplifier. Okay, so the amplitude of this, since the amplitude of the output is VDD by 2, so the amplitude of the Vin will definitely VDD by 2 by the gain. Okay, so that is the maximum amplitude that I can apply, because if I try to go for an input swing which is higher than this, then my waveform is going to get clipped. So the maximum amplitude of the input voltage of Vin is approximately, or I should say that the is approximately it is VDD by 2 into AB. So this is just rough values, I should say that. So this will give an idea of how big input signal that I can apply here at the input such that my output is not getting clipped. Okay. Okay, so this is the voltage swing property of the amplifier. Okay, I just need to make sure that these two conditions are satisfied in terms of the output as well as the input. Okay, so now we will see the input and output impedance of an amplifier. Okay, so before we are able to appreciate this point, let's try to see an amplifier. Okay, amplifier configuration, which we have discussed in one of the example in the previous class. So let's consider this problem. Okay, example problem where I have an input resistance Rs. Okay, so let's try to use this configuration again. So this is my amplifier, of course, with a source resistance. Okay, so just let's try to delete this one, and let's, instead of that, I'll just make it as VDD. Okay, I have a supply here, of course. Now suppose this common emitter amplifier is supposed to drive some load. Okay, I'm supposed to drive some load. Okay, it can be any load. Okay, so I'm supposed to apply this V out to this load. Okay, so now if I just connect directly, what will happen is, if I just direct connectly this V out, right, so my DC operating point is going to get disturbed. Okay, because you can see here in terms of DC, this current flowing through this one, right, so which was IC, will get divided. Okay, so it will get divided here, and it will disturb the DC operating point, or we may have to do the recalculation, or it may happen that if this is too small, then this may throw this transistor to the saturation region. Okay, which we don't want. Okay, so I just want to drive one load, so I just want to feed my output signal in this load, and I don't want to disturb the DC operating point of this whole amplifier. So we will use the same technique that we have done in the input. Okay, so I will be using a capacitor. Okay, I'll be using a capacitor which will be blocking the DC part. Okay, and which will be blocking the DC part, and it will be just passing the AC signal. So this is my coupling capacitor. This is coupling the AC, so this is also sometimes called as the AC coupling capacitor. Okay, so, and this is my, of course, my Vout. Okay, so yeah, and of course in this case only the AC will pass, so I can replace this one with the small letter variable. Okay, so because only the AC signal will be passing, and DC wise this is 0. Okay, so yeah, so this is how we drive a load using the common emitter amplifier. So this is a configuration of an amplifier with a load resistance. Okay, so now let's try to draw the small signal circuit of this holding and try to estimate the gain. So from our previous discussion, this is the small signal model of the amplifier when RL is not present. Now for RL, when the RL is present, we have put this capacitor, and for AC wise, this is like a short, right? So for a small signal analysis, if I'm adding this RL, so this RL will come here. Okay, R will come here, and if you observe the relation between RL and RC is that both of them are in parallel. Okay, so if you see here, the small signal analysis remains almost the same because I'm not changing anything in the input side. Of course, I'm not changing here also anything. So what I can just write is, instead of drawing this separate resistance, I can just write that my this resistance, instead of RC, it has become RC parallel RL. So that's the only change that I have to make. Okay, and if you see in terms of the gain, so in terms of the gain, so the gain will be V is equal to minus IC. So all the RC terms should be replaced with RC parallel RL. Okay, and rest remains the same. Okay, so now if we see in this, if we see in this expression, right, we have two terms are coming. Okay, my RL term is coming as well. This RS term is coming. As a result, the gain is very much dependent on the RS as well as RL. Okay, so for this kind of circuit, of course, it is very simple and we can solve it and you can do it. But for larger circuit, we will see that, it may be difficult to again and again solve the same thing for different value of RL and RS. Okay, so in other sense, the other way to look it also is, you see this RL maybe some, let's consider this RL is a speaker. Okay, I'm driving a speaker, and this is a microphone. Okay, this is a microphone. Okay, so we can consider that we are driving some speaker, and this is my microphone, and this is the amplifier. Okay, so most of the time what will happen is the amplifier will be designed by some other person, and the speaker or the output RL may be designed some other company, and also the input may be designed by some other company. So it becomes very handy. So instead of, if I'm just the user of this amplifier, instead of trying to know what actually it is made of course in these days I have only one BJT, but in many cases it can have multi-stage and multiple BJT. So is it possible that this whole thing can I approximate with some equivalent model? Of course not approximation. Can I have an equivalent model of this one which is simple enough and which is very basic? Okay, so this is what we will be seeing in this next discussion. Okay, so how can I get an equivalent model of any amplifier, right? Some model by which I can get an equivalent model, and we will see that using that equivalent model technique, we don't have to do all the calculations again and again. Of course, we can get the gain from V out to V in here by doing all this small signal analysis. So in the equivalent model analysis, what we are going to do, that we are trying to get an equivalent model of this one, and again we will try to find out the V out by V in using that technique, and we will see that the gain that we are going to get is going to become same if we use this the conventional procedure and also the equivalent model procedure. Okay, so the equivalent model of an amplifier. So what is an equivalent model of an amplifier? So any amplifier, it's like a black box. Okay, so and of course we'll have an input. Okay, V in the amplifier, and of course the V out. Okay, of course these are the small signal parameters only with respect to the small signal or the small change. Okay, and of course this V in and V out are with respect to the ground, which I am not showing. So when I'm calling V in and V out, we are referring this signal with respect to the ground. Okay, so I have my V in and V out, and it can be any black box. Okay, so this black box, right, this black box can be modeled by just three parameters. So what I can model is something like this. I'll have a resistance here, and this is called the R in, and I will have a voltage dependent voltage source. Okay, so which is AV into V in. Okay, V in is the voltage here. Okay, and I have another resistance which is basically the output resistance, which is also called as the R out. Okay, so just by using these three parameters, of course I have a ground here. Okay, so just by using these three parameters, which is R in, R out, and AV in, I can represent any kind of amplifier. Okay, so currently we are discussing the common emitter amplifier, and we will see some other different kinds of amplifier as well. And amplifiers can have one stage, two stages, multiple stages, but any amplifier, the whole black box, can be represented using these three parameters, which is the R in, R out, and AV. Okay, so we will see that. So R in is basically the input resistance, and R out is also called as the output resistance or the output impedance. Okay, and AV is the gain. Okay, so now given a black box, given a black box, I don't know what is inside this, right? I know that I have only a two port. Okay, this is my input and this is my V out, right? I don't know what is inside. Okay, so I am supposed to estimate what is the R in, R out, and AV of the this amplifier. So to do that, we just need to apply some stimulus from the outside, right? We just need to apply some signals from the outside and see how this whole black box is responding. Okay, so depending upon how this black box is responding, I can find out this parameter R in, R out, and the AV. So let's see how to do that. Okay, so now if you see here, if I apply a signal, maybe if I apply a signal, maybe I'm applying a signal here, stimulus Vx. Okay, so now the Vx, so V in is equal to Vx here, and if you see here, okay, if you see here, this is also AV into Vx, and here also, if I am not connecting any load, if the load here is infinite, so no current is flowing through this, so here also it is my V out is AV into Vx. So now if I divide this ratio of V out by V in by applying the signal, so my V in is of course Vx, and the V out that I'm getting is AV into Vx. Okay, Vx get cancelled, and finally I'm getting my parameter AV. Okay, so to get this parameter AV, what I should do is that I should make sure that there is no load resistance RL connected here. It should be infinite. Okay, so and by just applying the signal Vx, and I can observe the V out, and if I just divide these two ratio, I will get my parameter AV. So this is very simple. Okay, so how to get the AV? So AV is basically the gain when there is no load. Or basically my RL is infinite. Okay, there is no load at the output. Okay, so this is what we have, how we have estimated the AV. Okay, AV parameter. Okay, now let's see how to calculate maybe this R in. Okay, so to calculate R in, it is very simple. You see, if I have applied this Vx, and if I observe what is the current going inside this black box. Okay, and of course in this case also we should make sure that this RL is also infinite. Okay, so then what will happen is this will give me my input impedance. So for that case, I just need to apply this signal Vx at the input node and see what is the current going inside it. Okay, so apply signal Vx, apply a signal okay, so I just need to apply a signal Vx at the input and observe the Ix, and see by simple Ohm's law we know that what is R in will be equal to Vx by Ix. So this is how we can get the input impedance of the equivalent model of an amplifier. Okay, So now, okay, we have estimated R in and AV. Looks like these are very simple parameters. So now we want to estimate R out. Okay. So if you see this R out is at the output side. Okay, R out is at output side, and of course here also I can apply some signal at the V out this node. Okay, and see how it is behaving. Okay, so let's consider that. Let's apply a signal again Vx at the output node. Okay, and let's observe what is the current flowing through this. But if you see here, this factor, which is a voltage dependent voltage source, right, it is dependent on this V in, right, this is a voltage dependent voltage source, it's going to interfere this current Ix. Okay, so that means what I need to make is that I need to short this whole thing, okay, and make it zero. Then what will happen is, if I short this whole thing, then my R out will be nothing but the Vx by Ix. So just by observing what is the current that is going inside, by applying a signal Vx, I can find out my R out. Okay. Now how do we make this zero? So to make this zero or make it short, I just to make this V in zero. Okay, because I don't have any option to make this AV zero, because I cannot touch this internal parameter. But yes, I have an access to V in. So what I need to do is that I just need to make this V in 0. Okay, V in 0, and this will be 0. So my Vx by Ix will give to me R out. Okay. So again, apply a signal Vx. Output node, and again observe Ix. Again here also, of course, the RL should not be there definitely. Okay, and my R out will be here. Again the condition here, again the other condition is that my V in should be 0. Okay, so V in also should be 0. Okay, I should be shorting this one, so by that I will be able to estimate the output impedance of this amplifier. Okay, so this is how we have estimated the three important parameters: the input impedance, the output impedance, and the gain in the no load condition. Okay, so just to conclude this discussion, so the Rin is called the input impedance. Of the amplifier, and R out is called the output impedance of the amplifier. Okay. Okay, so now what we will do is, considering our common emitter amplifier, we will try to find out the this equivalent model of this common emitter amplifier. Okay, so whenever we are telling about this equivalent model, we are focusing only the small signal model. Okay, it is not on the DC operating point. We are just focusing on the small signal equivalent model. Okay. Okay, so this is my common emitter amplifier. Of course, this is my input node. This is my output node. Okay, and we are trying to find out the equivalent model. Okay, equivalent model of this one. Okay, so basically we want to get the equivalent model of this one. Okay, or more precisely, we have to get the small signal model of this one, then only we can get the equivalent model of this. Okay, because here we can see that it has both a DC and the small signal, so we need to get the small signal first. Okay, so this is the small signal model of this one. So basically we want to get an equivalent model of this one, not exactly this one. So better arrow would be, instead of trying to show this one, so better the small signal model of this one is this one. Okay, and we want to get an equivalent model of this one. Okay. Okay, So how do we get the equivalent model of this one? Again, so to find the gain, to find the gain or this AV, what we should do is we need to apply a signal here, okay, with RL is equal to infinite, okay. So that means my this AV is basically, this is my V in, okay. So it is basically the V out by V in with given the condition that my RL is equal to infinite. So this we have done multiple times, and in this case we know that this is minus IC RC by VT. In case you don't remember, please try to revise this part, okay. So gain, and for the input impedance R in is basically we need to apply signal Vx by Ix, and in this case also I should have my RL to be infinite, okay. So, and of course if you see here, if I apply a signal Vx here, okay, Vx here, and if you see the current flowing through this, it's very clear that the input impedance will be RB1 parallel RB2 parallel R pi. So it is very clear, right? So you can do this simple maths, but just by observation also we can see that these two resistance are coming in parallel, okay. So R pi, so this is the input impedance. So whatever the current that is going here, so it's easily divided based on the ratio, and you can see here from this node these two are parallel, okay. So this is the input impedance. Now what about the output impedance? So to get the output impedance, we need to connect this to the ground, okay. This would be 0, and if this is 0, that means of course there is no current here, no current here, so this will be off, okay, because my IB will become 0, and the only resistance that is remaining is RC. So in this case my R out, which is basically again Vx by Ix, given that my V in is equal to 0 is equal to RC. So these are the three parameters, okay, and these are the three parameters of the common emitter amplifier, okay. So now let's write it down. So these are the three parameters, okay. So now this is my common emitter amplifier, okay. This is how my common emitter amplifier is looking, and these are the three parameters. This, the AV is given by minus RC by VT, R in is RB1 parallel RB2 parallel R pi, and R out is RC, okay. So now I want to know, okay, if I connect a source resistance at the input, okay. So if I connect a source resistance at the input Rs, okay, and let's call it to be V in dash, okay, and I'm having a resistance RL at the output node, okay. So this is let's call it as maybe V out dash, okay. So after connecting this RL, I want to know the gain, finally gain, the AV dash, which is basically V out dash by V in dash. So this is what I am supposed to estimate. So yeah, so basically this configuration will be same as the one that we have discussed here, okay. So with the load resistance RL as well as the input resistance RS. So I am supposed to get the same gain expression even using the equivalent model, okay. So I am supposed to get the same expression, okay. So let's try to write down the expression of the gain using this equivalent model, okay. So now if you see here, this here my V in is a simple voltage division of R in and Rs. So here my V in is equal to it is voltage division of R in and Rs into V in dash here. So now whatever is coming here, V in it will be coming here. So it is AV into V in here, we know that, right? AV into V in. And my V out dash also will be the voltage division between the R out and RL of this voltage, okay? So my V out dash will be equal to RL by R out plus RL into AV into V in, okay? So I can just substitute these intermediate terms V in here, okay? So therefore my V out dash will be equal to, right, this is RL into R out plus RL AV into this V in, right? Let's call it this 1, okay, which will be basically R in by R in plus RS into V in dash. This is from 1, okay? So therefore if I just divide, right, my AV dash, which is V out dash by V in dash, will be equal to AV into RL R out plus RL into R in by R in plus RS. So now let's substitute this RL, of course not RL, R out, R in and AV for the common emitter amplifier, okay? So the AV in this case is minus ICRC by VT, R in is RB1 parallel RB2 parallel R pi, and R out is RC. Okay, let's substitute these values, okay? So if I substitute this value, my AV is minus ICRC by VT, and in this case my R out is RC, so RC plus RL, and here I have my RL, and we know that R in is RB1 parallel RB2 parallel R pi, and R in is again, I am just rearranging it, I am bringing the RS this side, so again it is RB1 parallel RB2 parallel R pi, okay? So if you see here, if I just bring this term RC here, right, just from this position to this position, you will see that this is nothing but RC parallel RL. So finally what I'll get here is minus IC by VT into RC parallel RL, okay, into this whole term which is RB1 parallel RB2 parallel R pi RS plus RB1 parallel RB2 parallel R pi. Okay, so now if we observe this gain, which is AV dash, okay, this gain expression is same as the one which we had got before, which is this one. So so this one, okay. So whether by using an equivalent model concept of this amplifier and solving the whole thing, right, whether considering this as a black box and finding out this R in and R out and AV and solving it, right, solving it basically 2 times, or directly solving it, right, by considering the whole entire equivalent circuit, if our procedure that we have followed is same, then we are supposed to get the same result, okay? So this is very important, okay? So now one may ask this question, that why we need to go for an equivalent model. So we will see that as we go ahead, as we progress, we will see that using an equivalent model makes lives much easier, especially when we have to solve complicated parameters. So basically it becomes useful if I have multi-stage amplifier, then expressing each of the stages with an equivalent model and then trying to solve the whole thing makes lives much easier, okay? So this is the main reason why we go for the equivalent model of the amplifier, okay? Also, it also gives some insight of what happens if my input impedance is small or large, or this we will see, especially when we will be discussing other configurations of the amplifier. So this also help us to give an insight of when in which situation this amplifier can be used, right? Depending upon what is R out and R in. Okay, so that's why understanding the input impedance and output impedance of the amplifier, or the input impedance or output impedance of the equivalent model of an amplifier becomes important. Okay, so we in this lecture we have understood the voltage swing, and we have understood the input and output impedance, basically the R in and R out of the equivalent model of the amplifier. Okay, of course the gain AV is the gain. Okay, yeah, so this is what we have seen in this lecture. In this next lecture we will try to understand the bandwidth. Okay, so we will see that how bandwidth is also another important property of an amplifier.